Alrighty, we are continuing our study of quadratics. The start thinking part is tying in quadratics with the real world. So it says a rock is dropped from a height of from a 500-foot building. The height above the ground is recorded every second. The resulting measures are recorded to the right. So you have this table over here, and it says determine if it is quadratic, linear, or exponential. So I always go, let's check if it's linear. If it's not, then you're halfway to finding out if it's quadratic, and then I go over and check if it's exponential. That's usually the way I do it. So this was down by 16, down by 48, down by 80, down by 112, down by 144. So the first difference is not the same, it's not linear. So then I go over and did the second difference, and I got negative 32 every time, which told me that it was quadratic because it had the second difference always being the same. The next thing it said was write an equation for this. This gets a little confusing if you didn't know the trick that you get your second difference and divide by 2. So if you take your second difference and divide by 2, that'll tell you the number in front of the x squared. That's not saying that's the whole equation, but that gets you a good part of it. So you could have y equals negative 16x squared, and then it says, hint, think about the original value. So that is making it go down, the negative 16x squared, and then it started at 500, so I put plus 500. Now, the negative 16 is talking about the effect of gravity in feet. If you were talking about the effect of gravity in meters, they would change that over to negative 5 as an approximate. So negative 16 is the magic number if you were dealing with feet, and negative 5 is if you were dealing with meters. The other thing is that this can actually be used by going over, if you drop something, you just take the amount of seconds it takes, square that number, and multiply by 16, and that will tell you how high the thing was that you were dropping the rock off of, or whatever it is. The next problem says, how do we adapt the formula if it is now a height of 400, and the only difference, the negative 16 stays the same because it's the same gravitational pull, and then you have 500 turning into 400. The next part is talking about, let's take gravity out of the situation, and let's talk about if you went over and shot a cannon from 10 feet off the ground and it launches straight up at a velocity of 406 feet per second, imagining there is no gravity, what would this look like? Well, since it is a constant 406 feet per second, whether it's between 0 and 1 seconds, 1 and 2, 2 and 3, 3 and 4, or whatever, we know this is going to be linear, which means I can kind of model my equation off of y equals mx plus b. So instead of y and x, they're using d and t, but we decided in class to go over and write this as an equation first, and then use the equation to come up with our table. So we knew you can do mx plus b or b plus mx, same. So in this case, we had the original of 10 feet, and then you're adding 406 feet per second. And like I said, it's linear because it is a constant rate of change. So we had that situation, which was taking gravity out. It was just if you shot it up, let's say this was in space, far away from anything that had a major gravitational pull, and then shot it up, it would just continue forever at 406 feet per second. Next. Now this next problem is slightly different. What they say is, hey, take a look at the table. This is when we do have gravity as part of it. And they were supposed to make 2 observations basically. And some of the observations students made was they both start at 10. They're both going up. One of them seems like it is slowing down as it goes up. So those were the major observations that students made. This graph shows the 2 different paths. So basically, one of them just went up. Not everything had a force going up. There was no force counteracting it, trying to pull it back down. Whereas now, when gravity is in there, you have the force pushing up, and then you've got the gravitational pull. And at some point, as we know, it gets to its highest point, and then it comes back down. So you can see the height as it changes. And you can also see that the graph looks like a parabola. It's got that U shape, so we know it's going to be a quadratic here. A few things that we wanted to look at, that we wanted to put a name for, is that highest point we talk about as the vertex. So the vertex, if you figured out what that point was, I think it was like 11, 12, 12.5, 2600 or something like that. That means at 12.5 seconds, it is going to be 2600 feet high. you were supposed to come up with an equation. The equation we already had was d equals 10 plus 406t. That was the original height, and then it just had a force pushing upwards. And the students had to figure out how can we adapt this so that now it has an equation that accounts for the gravitation aspect. So all they did was have to stick in the minus 16t squared. That's the part that's pulling it down, the gravity, and then you have the original and you have the initial upward velocity. So we came up with this equation of y equals negative 16t squared plus v sub 0t, which means original velocity, upward velocity, plus h of 0, which is the original height. You can use this as long as you're dealing in feet. If you're dealing in meters, you should have negative 5t squared plus v sub 0t plus h of 0. And that would be if it was meters per second. Kind of a cool formula you can use if you throw an object up in the air and you have a certain upward velocity and a certain height. You can kind of figure out a few different things, like when it hits the ground, how high it goes. And not only that, but if you have only one piece missing, you could solve for the initial velocity, or you could solve for the original height if you had the other stuff. Now, the only other two things we had here was we've always talked about them as x-intercepts, but they now talk about them as zeros. So in this case, there's two zeros, but technically, since we're starting at 0, 10, a y-intercept of 10, I know my other 0 or my other x-intercept is going to be in the negatives, and it's going to make no sense. And then the only 0 that makes sense is the one that is a little bit past 25, it looks like. It's kind of hard to read that for me. And that would be when it hits the ground, when it is 0 high. We then looked at this problem right here. They gave you the equation 50 plus 312t minus 16t squared, and they asked, what is the 50? We know the 50 is the original height, the 312, is the original upward velocity, and then negative 16t squared is accounting for gravity. Describe the shape of the graph. It is a parabola, so we know it's going to be quadratic. And then it says estimate the maximum height. On here, it looks like the maximum height is going to be 1,571 at about 9.75 seconds. The other thing was, it says when does it hit the ground? While you will have two zeros, if you just followed the path, it would bring you into the negatives, and that one would make no sense. So we only used the positive one, which was 19.65. And then it says, what's the appropriate domain for this function? It goes from 0 to 19.65. So 0 seconds up to 19.65, and then it's on the ground. So the model, that just doesn't make sense. It also doesn't make sense in the negatives. Let's go ahead and go over the homework. So on the first problem, it says the height of the diver above the water is given by the function h of t equals negative 5t squared plus 10t plus 3, where t is measured in seconds, and h of t is measured in meters. Select all that are true. So the negative 5, once again, is because now we're dealing with meters and not feet. So it says the diver begins at 5 meters above the water. That's incorrect because that is not the constant value. That is having to do with gravity. The diver begins 3 meters above the water, which is true. That's the constant. The function has 1 0 that makes sense in this situation. That is correct because you know that it's going to have a y-intercept of 3. So the second 0 is going to be in the negatives. That just doesn't make sense. D, the function has 2 zeros that make sense. We already said that's not right because you're going to have a negative. The graph that represents h starts at the origin and curves upward. It does not start at the origin. The origin is at 0, 0, and we know we're starting at 0, 3. And the diver begins at the same height as the water level, which is 0, which would be incorrect. Number 2. The height of the baseball in feet is modeled by the following function. We're back to that negative 16 because we're dealing with feet. About when does the baseball reach its maximum height? To me, that looked like about 1.8 seconds. How high would that be? Looks like a little less than 60 feet. About when does it hit the ground? At about 3.75 seconds. And that is called a 0 or an x-intercept. The next one asked you to use Desmos, and you were supposed to put both of these in. Usually with Desmos, I change the f of t to y, and I change the t's to x's. And when you graph these, I drew a little bit of a graph of what they looked like. Hopefully you actually use Desmos. and you find that B is going to hit the ground first. So the next one, we're looking at this. I changed it to be -16 because I had not realized that they were saying -5 for meters. So the -16 on yours was me changing it to feet, which I shouldn't have done because it was actually in meters. It should have stayed at -5, but it doesn't really change the problem because it says which object was launched with the greater vertical speed. And you should know which part that is. That is the part that has just the t, not the t squared. So it's 25 versus 50. So B is correct. And the next one says which object was launched from the greater height. And that would be the constant value. You're comparing 25 with 50 again, the last number though, so 50. Number 5, a rocket is launched in the air in feet, is modeled by the function h. Here is a graph representing h. Select all that makes sense. A, the rocket is launched from a height less than 20 feet above the ground. So when we're looking at this, it does look like it's less than 20 feet above the ground. The rocket is launched from about 20 feet. Nah, that does not look like 20 feet. The rocket reaches its maximum height after 3 seconds. That seems right. The rocket reaches its maximum height after 160 seconds. Nope, that would be the height of it. And the last one, the maximum height is 160 feet. Yes. Now this next one here was just a review problem. It was students on the midterm had trouble going over and solving these compound inequalities, so I wanted to give one of those. You would subtract 4 from the middle and then both sides, and then when you divide by -2, you have to switch your symbol. That is going to tell you where you put your open and closed dots. You would graph x is greater than or equal to -2, and x is less than 12, and wherever the overlap is your solution. Hopefully that made sense. Like I said, this whole unit is about quadratics. Thanks for watching.